All right, let's get started.
Recording?
Yes. Okay, so what are we working on? We're working on closed form rules for rate functions derived from accumulation functions, right? So we start with exact accumulation, and we figured out how to come up with an open form for rates, and now we're working on some rules to get closed form rate functions. All right, so here's the rules we have so far. A constant function, a constant times another function, x to the n, and the sum of functions. Okay, so this is the four rules we have so far. So what is what is the definition or the difference between an open form and closed form? And then here's, for this particular one, xn, I want you to write them both out. So take a minute. So first of all, what do we mean by an open form function? And what do we mean by a closed form function? Let's review that. So with the person next to you. And then for this particular one, x to the n, write out the rate function for x to the n in open form and in closed form. So see if you can do it without shuffling through your notes. See if you can collaborate with the person next to you and kind of remember it, rather than just looking it up in your notes and reading it. Okay, go.
Those forms, the one with the approximate that's constant, which is very small. So I kind of that's good. Because you leave h out. When you still count h, it's not really small. So that's like an approximate. Yes. So I just that's saying h is small. Approximately. That's yeah, I wasn't sure on it.
I'm confusing myself now. Thank you.
Okay. So aside from x to the n, just in general, what do we mean by open form, an open form function? Aaron. So the process of what it's supposed to mean? Oh yeah, what do you think it is?
I said it was or the thing was for our x and x was x of n, the n is any positive number at least in
Okay.
which so that basically it is like
So what's x to the n? Is that what you're saying?
x to the n is any positive number.
Okay, so what we want is the rate of x to n. Austin, you were going to talk about what open form was.
I was gonna say it reflects the process.
That's right. And that's what you said. So it reflects process. Or shows the process. In this case of what? Accumulate a rate from accumulation. We're talking about rate from accumulation. So our open form is going to reflect that process view of the meaning behind this rate function. And what about closed form?
That's referred to as the quick answer. Quick.
Right. So it's like It's a standard function. Yeah, and the advantage to that is, Ryan? Quick results, right? Quick results. We plug in X values, we get the rate of change, right? Plug in X's, we spit out rapid fire rates of change. Okay? So never lose sight when we talk about open form or closed form. So open form shows the meaning, it shows the derivation, it shows the process. And closed form is the simple function, or relatively simple, that spits out results rapidly, right? And now we're talking specifically about rate from accumulation. Okay, so now what is the open form rate function for x to the n? Open form rate, yeah, Kevin.
Well, I said it was the integral from x to a of x to n.
Okay, so if you have an accumulation, you're going to take the integral to get the rate. What do we think about that? Agree with that? Christian, what do you think the open form is for the rate function for x to the n?
Open form would be f x minus h minus f of x over h, and then you do some stuff with that.
Okay, so but we're talking about x to the n. So I didn't necessarily call this f. We got x to the n. Aaron, over here.
Would it be as h approaches excuse me, as h approaches 0, x plus h to the n
Okay.
minus x to the n over h.
Okay, what do we think about Peter? You agree with that? What, Shana? Go ahead.
Isn't it just the integral of x to the n?
Oh boy. Did everything fall out of our brains over the weekend? Okay, how did we get rate from accumulation? What was the general idea? What's the general structure? Rate from accumulation. The general structure of rate is? Change in y over, that's our rate, right? It's change in y over change in x. And so what's change in y for x to the n? So Aaron got it. Okay, do we need a limit for this notation? So for this rate, remember we talked about last time, this rate notation is just, it can be it doesn't have to be necessarily for h small. So okay, so h could be 1, h could be 0.5, and we get an average rate function, okay, an average rate function. So if you haven't learned, this is what we call the definition. This is the definition of our average rate function, and that's the open form for rate of change for this particular function x to the n. Okay, so if you haven't learned this yet, quick, learn it. It's not integral, right? Integral is accumulation from rate. We start with rate. The integral is summing up all the bits of change given the rate. So integral is when we're building an accumulation function from rate. Okay? So what about the closed form? So what we're saying now is the closed form occurs when we say we let h get sufficiently small. When h gets sufficiently small, what is our closed form rate function for x to the n?
The limit. I have a question.
Okay, question.
I want to try to not go in and just be the limit as h approaches 0 because it's getting really small.
Okay, and then what did we find that was? Jamal. Yep, so that's your rule. And x to the n minus 1.
And I have a question.
Uh-huh.
Like your equal sign says essentially equal to?
Yeah.
I thought it was equal to that.
Well, this is our notation for R. So our notation for R means the average rate function, which we allow for h to be, say, 1 or 0.5. But then when h gets sufficiently small, then these are essentially equal.
Okay.
Yeah. Okay? And so what about exact rate in open form? So now we want to get the exact rate function in open form. So this is an approximate, right? This is approximate rate in open form. What about exact rate in open form now? Alexander, how would we?
The limits of h is approaches 0.
Of that thing? Yeah. Yeah. So now when we put the limit on there, we get still open form, but now it's exact. Now it's the exact rate function, and that was our notation for exact rate function is this d dx. Okay, or d x to the n dx. And then what about the exact form in closed form? So the exact rate of change in closed form for x to the n.
It would be the same thing
As what?
as x, or n x again as well.
Yes. That's it. That's it. Okay, so we're kind of giving all the possibilities of exact and approximate and open and closed form. So I want you to categorize these as exact, approximate, and open and closed. Go. So talk to the person next to you. So what's exact? What's approximate? What's open? What's closed? Go. No, that's not all I did. There's a big difference between this and this. Because it's coming from the average rate function. So, right, the average rate function, when h is sufficiently small, results in this. So, this is yeah, it's a little, yeah. Okay, what about open form? Jonathan?
Open form is everything on the left side.
Like that? Those two?
Yep.
Yeah, so our left column is our open forms, right? Okay, and then so closed form? Over here. What about exact versus approximate? Brent?
Approximate is the top row.
Top row?
Exact is the
Got it. Right? Is that what you came up with?
Yep.
Okay. Cool. So just reviewing this, what does that mean? Open and closed. Any questions? Anybody have a question? Yeah.
Whenever we'll see like D over D of X,
Yeah.
should we automatically always assume that it's exact?
Yes. That notation means exact. Yes. Right. That is our exact notation. And this can mean either, right? So it's coming from the approximate rate of change from the average rate of change. But we know if h is sufficiently small, we get the exact. And that's what's happened here. Yeah, Jamal.
I don't understand why someone that's closed and approximate is approximate. Should it just be
It is, okay, it is exact, okay? This is the exact because it's that, right? But it's coming from our approximate, it's coming from our approximate rate function when we let h get sufficiently small. Does that kind of help?
Yeah.
But you're right, this formula is the same as this. It's the exact formula, okay? But it's essentially equal to this when h is small. So that's why I'm putting it in the approximate category. Okay, other questions? All right, so how about this one? So here's something new, square root function. So before we do the square root function, we need a rule from algebra we've seen before, that a minus b times a plus b is a squared minus b squared. This is going to help us. So what do we want to do? We want to derive the rate of change function for what we're calling f. Okay, so how do we start? So everyone, how would we start to figure out what this closed form rule is for f, which is the square root of x? Okay, working out with your partner. So just how would you start? How would you get started figuring out what the closed form rule is for, is that a question or a response?
It's kind of like a comment.
Comment, okay?
I mean, we know how to do this since we've taken calc before. We're not allowed to use rules.
We're not to do what?
We're not allowed to use rules.
We're going to learn them all again. For this particular thing, so you want to use the power rule. Yeah, we're going to do that in a second. But how would you do it if you didn't know that? That's the question. How would you get started?
I'll ask him. Are we allowed to
No, you can't use another rule. So we want to figure out what this is. Okay, Shannon, how would you get started on this one? No. What were you doing? Okay. How do we get started if we want to form a new rule? Yeah, Melody.
I put it into instead of square root, I did x.
Okay, no, so you guys are missing the point. Yeah. Kevin.
So I did, like what he said over there, just add on.
Okay.
The square root of x plus h minus the square root of x over h.
Right. We always use the open form to prove these rules. You always use the open form. So if you missed that, you didn't do this just now, somehow we gotta like shift your brain. If we want, this is the trusted form. Open form is trusted, right? And so if we want, and all the rules, all the closed form rules come from the open form. All the closed form rules come from the open form. Okay, so here's where we got to get these square roots off, and here's where the algebra trick comes in. So we start by, if we want to use this, what do we want to multiply the top by? No, but the opposite, right? So we have a minus b here, and so if we multiply by a plus b, here these squares are going to get rid of our square roots for us. You see that? So we got a minus b. And yeah, it's called the conjugate. And so in the numerator, so why is this going to help us? Because then when we have these squares, a squared and b squared is going to get rid of the square roots. Okay? So we're using this algebra rule in the numerators. But if we multiply the top by the square root added to the square root, we also got to multiply the bottom, so it doesn't change the value of the ratio. It's just like multiplying by 1. Okay? And so when we do that, we get a squared minus b squared, which is x plus h minus x in the top. And that leaves us just with h in the top. And we had an h in the bottom. And we get that thing to simplify, and we end up with, don't scribble frantically. Watch, maybe try to do it yourself later, watch the video. So don't just try to scribble this frantically. Okay, so we get h in the numerator, which simplifies with h in the denominator, and then when h gets sufficiently small, we get 1 over square root of x plus square root of x, which is 1 over 2 square root of x. Okay, so many of you wanted to do this first. You wanted to start by saying f of x is x to the, and so Melody, what did you want to do with that?
I did your close form, but you said not to
Okay, and so what was that?
do. I did 1/2 x to the negative 1/2.
Okay, so we could say d 1/2 x to the negative 1/2. And what does x to the negative 1/2 mean? X to the, which equals? So we got the same thing. Okay, so this is our showing how to get the closed form rule for square root of x from the open form. And then this is, what is this doing? This is verifying that the power rule works for values other than whole numbers. See that? So this is showing that that power rule works for other values other than just like x to the 8th and x to the 10th and x to the 5th. Okay, so it's seeming that that power rule also works for a fractional exponent. Yeah.
I'm sorry. For like when it has h over h times 1 over the x, the square root of x plus h plus square root of x. Did you just take the limit to get from like that step back down? Is that why the h disappears?
This is for, so whenever we use the essentially equal, so we're saying when h is sufficiently small.
Okay. So I didn't understand.
Yep. Okay, so let's practice this is called the x to the n is called the power rule. So right here. So the power rule we know is the closed form for the rate for x to the n. Okay, so now we're going to practice okay, try these. So find using the power rule, just a quick exercise here. Using the power rule, find the closed form rate of change function for these, which we're seeing that it works for any value, any exponent of x, not just whole values, like in polynomials. Okay, Janae, did you get the first one?
16.3x to the power of 16.3.
What do we think? Agree? Yeah, you literally subtract 1. You literally subtract 1. Okay, about x to the 0.4. Ross, did you get that one?
Okay. 0.4x to the negative
0.4x to the negative 0.6. What do you guys think? Yeah, literally subtract 1. You literally subtract 1. X to the minus 20. This counter over here.
Negative 20x
To the negative 19. Yeah, literally subtract 1. You see? Negative 21. So yeah, it's not 1 closer to 0. It's you literally subtract 1, no matter what that starting exponent is. Okay, so we have another rule for square root of x, which we could also use the power rule. So both using the power rule and deriving it, we get the same thing. And so square root of x is a common function. So 1 over 2 square root of x is a closed form for with the accumulation function of square root of x. Closed form rate. Closed form rate. Any questions on that? Okay, so this is important to have this rule, the square root and the power rule at our fingertips, so we can just do that, find these rate functions quickly. It's a little dry though. Okay. So let's look. This one's a little more interesting. Okay. So what about b to the x? What's the rate function for b to the x? What do you think? Closed, yeah. All right, so xb to the x minus 1. What do we think? So the question is this the same as x to the n? Are they the same so that we can apply the power rule to b to the x? So where's the input here? Where's the input here?
The number being exponential.
That's called the base, right? Yeah. Yeah. No, that's right. It's exactly right. Just need a quick term for it, right? So the number being raised to the exponent. Okay? Where's the input here?
It's the one
The exponent.
Okay, I think it's actually going to be I think it's going to be dx times b to the x.
Okay, so maybe is it from a past? You've seen this in the past, maybe?
Yeah, it's like, well, I'm just kind of equating it to when you take the derivative of e to the x.
Okay, so yeah, so we haven't gotten there. So we're starting from scratch. We're starting from the ground floor here. Okay, so what about this? So we're back to, what about this? So are these the same, about the same covariation, x to the n and b to the x, in terms of the covariation of x and y? The same or different?
Different.
Radically different, right? Totally different. In this, the input is the base. Okay? And here the input is the exponent. That makes for totally different covariation between x and y, how they change together. Okay? So millions of calc students have tried it. It does not work. Okay? It's not the power rule because we're starting with a totally different kind of function. Okay? So what are we going to do? How are we going to get it? Yeah, James.
Well, we need to put it into the
Open form. Can you tell me what the open form is?
I have no idea. I was going to ask.
Oh, no, you can do it. So what's the open form of, if you just had f of x, how would you write the open form?
It would be x plus h minus x over h.
What about x plus h? It's not we know what the inputs, we want the outputs, right?
Yeah.
So, no, it's okay. There you go. All right, so we know that's the open form. So now we just got to apply what is f of x plus h for this function. So what is f of x plus h if our f is b to the x?
B to the power of x plus h.
He wants b to the power x plus h. Agree with that? That's what it is. So that's just saying, this is just saying the instructions here are raise b to the input. Raise b to the input. That's what this function is. So our input is x plus h. We're going to raise b to the input. Minus? Over? Okay. So now we know that we need to work on this. We need to kind of try to do some algebra or some kind of tricks on this to get something. Our problem is we want h to be sufficiently small, get very close to 0, and can't do it in the denominator, right? So the only thing we can work on here is this. So what can we do with b to the x plus h? We can do that. David, do you know what we can do with b to the x plus h? So you remember your rules of exponents.
You take the log.
No, I just want to rewrite this in a different form. What does this mean? What is b to the x plus h? What does that mean? Oh, we go back to applying this, yeah, power rule. Peter.
B to the x plus b to the h, or times b to the h.
Okay, he wants b to the x times b to the h. So really we're multiplying b together how many times? X plus h times, which is the same as multiplying b together x times, and then multiplying it by h more times, right? Isn't that what that is? That should make sense. But it should make sense, right? So an exponent just tells you how many times you multiply that base together. And so if we're multiplying together x plus h times, well then you could just separate it into the x times and then the h times, right? So we're just multiplying b together, x plus h times. Okay, what can we do with that? Factor out of b to the x. So in general, what is this showing us about the rate of change function for b to the x? What kind of, in general, is this showing us about the rate of change function? Sterling. I'm looking at this part. What's that? It's increasing exponentially. Okay, yeah.
It doesn't change. It is something different.
What is b to the x?
That's the
Yeah, it's original function, right? So the original function b to the x is part of its rate of change. You see that? But then we have this other part here. And so we know we're going to let h get, we're saying h is going to get small. So part of the rate of change function for an exponential function is itself. Okay, itself, and then we have this multiplied by something over here. So what happens as h gets very small? What about b to the h? 1, and so the whole numerator becomes 0. So it's like as h gets sufficiently small, just this part of it in the parentheses is like 0, what? Over 0. 0 over 0 is called an indeterminate form. And it's not that we can't determine it, it's just that it has different possibilities. Okay, there's different possibilities for what this could be. First possibility is 0 over 0. In some situations could be 0. In other situations could be a non-zero constant. And in other situations it could be very, like, go to infinity or negative infinity. So it depends on the context, it depends on the situation. It could be 0, yes, right, it could be any real number, or it could get infinitely large, or infinitely large negative. So, based on the fact that we're finding the rate of change of an exponential function, let's talk about 0. Is it possible in this case that it could be 0?
No, that would make our function 0.
It would make what 0?
I'll make our original function 0, so that would just be constant 0, so that makes sense. It's like 0, like your number multiplied by 0. It just makes it 0.
What is it?
F of x.
It's not making f of x 0.
On the rate of change.
Yeah, it's making the rate of change 0. So we have an exponential function, and if that ratio was 0, then the rate of change to that would be 0. Possible? No, we know exponential functions have if it's an increasing function, it's going to have a positive rate of change, and that's going to be changing. So, what about infinity or negative infinity? What would that mean? What about if that 0 over 0 was infinity or negative infinity? What would the impact be for what we're trying to do here? Is it okay? Is it possible?
Does that just mean the rate would get really, really big or really, really small?
Yeah, so it would mean that the rate was, approaching infinity. Meaning for any x value, if you change x a little bit, y will go to infinity. What do you think? Does this make sense? No, so that's just saying, yeah, as you change x, no matter what x is, you change x a minuscule amount, y goes to infinity. Doesn't make sense. So what's left? Okay, constant. All right. So our hypothesis is that that the rate of change function is some constant times b of x. That's our hypothesis. Based on eliminating the possibility of 0, just from common sense, it would make sense that it was 0. It wouldn't make sense that it was infinity. So that leaves that this ratio is some constant, and so that our rate of change function is some constant times b of x. So we want to investigate this. We want to investigate to see. And so we can use graphing calculator for that. Okay, so here I'm showing, so the blue function is, this is b is 7.5. So this is 7.5 to the x. Okay, and so then I've got the open form rate. Oh, it's up here. Okay, yeah. So f is the exponential function we're looking at. I got the open form rate, and I'm letting h be very small. And so when I graph that rate, I'll do the rate in red. You get this. So we come along here, and then with x, I can move this here to show different values of x. So let's look at here at x equals 0. What's the value of the function at x equals 0? And what does the rate appear to be? About 2, right? So according to our hypothesis, what do we think maybe the rate function is? So we're saying, Shayna.
2 times 7.5 dx.
So is it 2 times 7.5 to the x? Well, it appears that's true at x equals 0. And so this is our hypothesis that the rate of change is just a constant times the original function when it comes to exponential functions. So how can I check this? How can I check to see maybe if this is true?
Check the value of x.
Okay, good. So I'm going to come over here to x at, say, 0.6. Okay, I come over here at x at 0.6, and my original function is about, maybe? 3.35. 3.35, and so according to our hypothesis, we're thinking that red would be 3.35. Fumbling here. Okay, here we go. Maybe. Oh, it's taking a long time. Sorry. What do we got? 6.75. Okay. About twice as much? Yeah, so let's try, how about 0.2? 0.2. Original is? Yeah, about 1.5. If it is always 2 times, then this should be about 3.01. Let's do one more over here. Negative 0.4. 0.4466, so we expect this to be 0.9, right? 0.4466 would be about 0.9. Okay, so it seems like our hypothesis is correct. So let's try a different value of b. So let's just make b 4. Okay, so now here's b is 4. So how can I figure out what this constant is that gives us the rate. So if we multiply what constant times 4 to the x, how can I figure it out? What can I do? Kyle, any ideas? I'm asking what constant times the original function 4 to the x would give us the rate function.
Maybe 1.5.
And how are you seeing that?
Because the graph is 1.5 times larger than the original.
And where are you coming up with 1.5?
1 times 1.5 is 1.5, and so the red line goes across the line.
You're looking at x equals 0?
Yeah, and x.
So at x equals 0, let's find out what is the red one. The red one is? It's actually 1.386. So how could we figure out that value without, if say we were only looking at positive values of x? How could we come up with what this 1.3, what is it, 1.386? So yeah, so we can come here and we can say, oh, the function's 1, the rate is 1.386, so that seems to be the multiplier. But say I was only allowed to look at positive x values.
Take the ratio
Ratio of what?
of the y values of the two graphs at the same x.
Okay, good. So it would be the ratio of f to r or r to f? Melody, what do you think? Ratio of r to f or f to r would be this multiplier. Did I lose you? Zoe, what do you think? R over f. Yeah, because the number that we had to multiply f by to get r would be the ratio of r to f, right? And so I have that set up here, right, in the next line. So here at, what was it, x is at now 0.92. At x of 0.92, I've got that ratio of 1.386. So what will happen to this ratio, if our hypothesis is correct, what will happen to that ratio as I change x? What's that? Oh, was that you, Shannon? Yeah, it should stay the same. If I change x, then this ratio, or this multiplier on the original function to get the rate function, according to our conjecture, should stay the same, right? So look what happens. See that? Doesn't matter what x value I pick. This is very strong evidence here that it's true that the rate function is a constant multiple times the original function when you have an exponential function. Is this making sense? Okay, let's try another one. So how about when b is 1.6? B is 1.6. What's different about this one now? So now we're doing r of 1.6 to the x. So what function is the rate function of 1.6 to the x? Linwin, can you tell me? What's this rate function for the exponential function 1.6 to the x? Kevin?
It would be 0.47 times 1.6x.
He wants 0.47 times 1.6 to the x. Kaylin, you agree with that?
Not sure yet.
Not sure?
You say it again?
He wants 0.47 times 1.6 to the x. Nicholas likes it. Yeah, because this ratio is our multiplier on the original function that will give us the rate. So 0.47 times 1.6 to the x. Okay. And how is this one different than the others? Different constant, that's true. But the other two... What's that? X starts with a negative? Well, I can change x and make it negative or positive. What's different about this rate function?
Is it that it's being like It's gonna be multiplied by 0.47, so that means that the rate is like lower, I guess, than
Right.
The rate
Yeah.
is-
It's a fraction of it instead of a greater value, right? So here, these constants were greater than 1, and this one's less than 1. So the rate's now a fraction of. Still a constant multiple, but now it's less. The rate is less than the actual function, which begs a question. What question does this beg? Something
rate is
interesting.
some constant multiple of the accumulation.
Well, we're saying that's, we know that, but there's something very interesting to look at here. What is it?
means that at one point they're gonna have to like
Equal.
What's that?
What did you say?
At what point are they equal?
Yeah, you see somewhere in here there's a certain exponential function whose the constant to get the rate is 1, so that they're equal, so that the rate function equals the original function, or this constant we're talking about is 1.
How is that possible?
What it means is the function that the rate at any given x value is the same as the y value. Now it's different units. It's not the same units. Y is still your accumulation unit, and the rate is still y per x. So it's different units, but the value is the same. Does that help? Yeah. Okay, so let's take a look here. Where is it?
2.7.
All right, looks like it's about 2.7. So let's zoom in on that. Let's make our slider, to make this fine-tune this, 2.6 to 2.8, so we can get a clear idea of where this is. Okay, so what am I looking for when I slide this b? What am I looking to get? No, I want to be mathematical.
Ratio of rate to be 1.
What needs to be 1?
R.
Yeah, that ratio we want to be 1. So I'm going to get as close to 1 as I can. I think I can get like 0.9999 or something. There we go. So what is this value of b that does that? 2.7818. So r 2.718 to the x, that rate function is 1 times, or it's the same as the original accumulation function. Okay, so this number is actually a number like pi. It's an infinite non-repeating decimal. So this is only an approximation up to the thousandth place. It's a number like pi. It's actually 2.718281828459. What do you think I do in my spare time, you guys? Okay, I have a trick. If you want to know the trick, come to my office. Okay? There's a nice trick about the presidents. Okay? The presidents helps you remember this. But anyway, it's a number just like pi. It's an infinite non-repeating decimal. And it's called the natural base, E. Just a number just like pi. So that's this E. So what is this E? It's the base such that that exponential function that has that base, its rate function has the exact same values as the y values, so the original accumulation function. Okay? All right, so let's summarize that. So this was our hypothesis, and we saw that it was true, that the rate function is a constant times the original function. And then we found that the particular function where the constant is 1 is for the base of this E, this number like pi. Okay, so the rate function of e to the x is just e to the x.
So if b is e, and then derivative of d dx is e.
That's right. If the base is e, then the derivative is the same function as the exponential function, original exponential function. Okay? Okay? Go back? Yeah, I'll go back. So there's one more rule here. So this rule now is that r of b to the x is k b to the x. Okay? And we didn't have time to show it, but k is, the constant is the ln of b. So I'll go back a second. Yes. You need to know the rules, yes. You had to, so for the mastery exam, you'll be doing just like lots of problems. So you have to know those rules by heart. So if you know those rules by heart, then you can write them.
What's up?
Phone information and classes.
Can I take this screen down? Do you want to see the previous one still? Sure.
Deal with D over dx. I mean, I know that's definitely going to have